Welcome back to this last video in this course, in which we are going to solve the second problem in the introduction about the implicit function theorem, and we shall give an important application about Lagrange multipliers. So here's the statement in full generality of the implicit function theorem. You can call it version 2 if you like, because it corresponds to version 2 of the inverse function theorem. So we have three Banach spaces, E, F, and G, with F and G isomorphic. And we consider a smooth map of two variables. Okay, it's a map from an open subset U of E times G, and that takes values in G, capital G, and we consider a point AB in the domain of small f, at which small f vanishes, and we assume that the partial derivative of f with respect to the second variable at the point AB is an isomorphism between the spaces capital F and capital G. So if f and g are not isomorphic, the whole discussion is empty. So always start by checking that f and g are isomorphic. Then, in simple words, we can solve locally the equation f of x equal y, and y in terms of x. So more precisely, there is an open neighborhood capital V of AB contained in U, and an open neighborhood W of A, and a smooth map of class C and G from W to F, such that G solved the equation, but in some sense it's unique locally. So what we can first say is that if x is close enough to A, then f of x, g of x is 0. So we have a solution. But conversely, if I know that x and y are sufficiently close to AB, and f vanishes at xy, then necessarily x is in W and y is this function of x. Okay. And of course, we have the implicit differentiation rule. So just differentiate the relation f of x, g of x equal 0 with respect to x and use the chain rule. So this is not difficult to. Okay, so don't confuse. So G is not the inverse of F. Okay, so it happens that we use the same notation in the inverse function theorem, but here actually we are going to deduce the implicit function theorem from the inverse function theorem, but we are not going to apply it to F. We are going to apply it to another map that I call F1. F1 is a vector field. It's a function of two variables, x and y, and has two components. The first component is x, is the identity, and the second component is f. So f1 is a map from E times f into E times g. Okay, so according to the discussion that we said about partial derivatives, the total derivative of f1 at the point xy can be thought of as a matrix of operators. So in the first place, I have the identity because this is the derivative of x of the identity. So it's like the rule of the Jacobian matrix, if you like. But instead of numbers, we have operators here. So the derivative of x with respect to x is the identity. It's 1, if you like. The derivative of f with respect to x is this in the second. So in the first column, I differentiate with respect to x. In the second column, I differentiate with respect to y. So the derivative of x with respect to y is 0, and then I get the derivative of f with respect to y. Okay, so what this means is that when I apply f1 prime at xy in the direction h1, h2, I need to put h1, h2 as a column vector and then multiply it by this matrix. So you can write the formula if you like. And now I evaluate this at AB. Okay, and it's now easy to check. You should be able to check that f1 prime of AB is an isomorphism between E times f into E times g. Okay, it's not difficult. So it's enough to check that the f1 prime at AB is both injective and surjective. Okay, because it's by definition continuous, and the inverse is automatically continuous. Okay, so if you want to remember that, suppose that you have numbers here instead of operators, then you get 1 partial derivative 0. So the determinant of this matrix is just the partial derivative of f with respect to y, and it's not 0. So this matrix is invertible. Okay, so therefore f1 satisfies all the assumptions of version 2 of the inverse function theorem, and therefore I can invert f1 locally, which means that I can find a neighborhood V of AB and the neighborhood W1, I would call it, of the image of AB under F1. But the image of AB under F1 is just A, F of AB, which is 0. Okay, and F1 is a CN diffeomorphism between V and its image, W. Okay, so if I let G1 be the inverse of F, then G is also a vector field. It has 2 components. But the first component is necessarily the identity. Okay, just check that. So G has 2 components. The first one should be the identity, and the second one I call it phi. Okay, so sorry, this is G1, not G. This is G1 of X. Okay, and if G is Cn, then all the components, both components are Cn. So phi of Xz is also Cn. Okay, and now I want to prove the condition, the first condition. What does it mean that xy is in V? Which means that xy are sufficiently close to AB, are in the vicinity of AB, and f of xy equals z. What does this mean? It means that the second component of f1 is z. Okay, the first component is necessarily z. So this equation is equivalent to this equation by definition of f1. And now, since we are according to the inverse function theorem, this relation is, so I can invert this relation now and write xy equal g1 of xz, okay? Because these 2 relations are equivalent according to the inverse function theorem. Okay, and now since the first component of g1 is x, then this equation is equivalent to saying that the second component of g1, which is phi of xz, is equal to y. So these 2 equations are equivalent. Okay, and now in particular, if I take z equals 0 and phi of x0 to be g, so g is as smooth as f, then I get this equivalence. Xy in V and f of xy equals 0 is equivalent to saying that x0 is in W1 and y equal to g of x. Okay, now I just need a neighborhood of A. So I introduce the map pi from E to E times g, which is to each x associates the couple x0. So this is like identifying E with E times 0. Okay, so and I take W finally to be the inverse image under pi of W. Then of course, since pi is continuous, W1 is open, W is open, and x0 belongs to W1 means precisely that pi of x is in W1, which means that x is in pi minus 1 of W1, and yeah, so therefore x is in W. Okay, so we have proved finally this condition. X and y are in the neighborhood of AB and satisfy this relation. This condition is equivalent to the condition that x is in a neighborhood of A, and we have this relation between y and x. Okay, so this is the content of the part 1, and conclusion 2 just is an application of the chain rule, as you know. Okay, we did it in the simple case in 1 dimension, but it's the same thing. So this concludes. So this implication from here to here is a kind of uniqueness, actually. Okay. Now, as an application, yeah, so as a remark, since AB is in V, of course, and f of AB is 0, then necessarily B equal G of A. Okay, so this is important too. Now, I want to give you 3 exercises. One about uniqueness, to make more precise what I mean by uniqueness. Okay, so if I have a connected set W prime contained in W, and a continuous map from W prime into F that solves the equation, okay, then necessarily H is equal to G. Okay, And this is not true without the connectedness assumption, actually. Okay. So this precises the notion of uniqueness. Okay. So try to prove that by using a connectedness argument, if you like topology. Okay. And second exercise, deduce the inverse function theorem, version 2, from the implicit function theorem by considering this map f1 of xy equal y to show we apply the implicit function theorem to this map f1 of xy, and then we have to find the inverse of f. Okay, so this is so the two problems are connected, actually. They are or the two theorems are equivalent. You can deduce one from the other. Okay. We chose first to prove the inverse function theorem first, but you could have proved the implicit function theorem first and then deduce the inverse function theorem. Okay, and last exercise, formulate and prove a global implicit function theorem in the same spirit of corollary 5.2. Okay, and now I'll end with an application to Lagrange multipliers that you may probably encounter in first year. So what is the problem? We want to maximize or minimize a smooth function subject to a condition. Okay, so for example, we want to maximize or minimize the map of three variables x plus y plus z when x and y z vary on the unit sphere. Okay, the unit sphere is not open, so it's not the same. In chapter 4, we studied some optimization problems on an open set, but here we want to optimize the function not on an open set, but usually on a compact surface. Okay, so we write this in this way: max or min over this condition. So this is what we call a constraint, okay, smooth constraint. So in general, if you have two smooth functions f and g from an open subset Q of Rn to R, then the maximization problem may be written as maximum of over x subject to the constraint g of x equals 0, or x belongs to g minus 1 of 0. Okay, so you can always think of g minus 1 of 0 as a surface. So instead of optimizing a function on an open set, we want to optimize it on a surface which is usually compact, actually. Okay, because compactness ensures that the maximum and minimum exists. Now, we are not going to care about saddle points. We could do that, but this is just an illustration of. You probably did that in first year, but I want to prove the Lagrange multiplier theorem from the implicit function theorem. Okay, so here's the statement. I would just consider one constraint, because you can consider several constraints if you like. Okay, but then you will have several Lagrange multipliers. It's the same idea. So consider two smooth C1 maps from an open subset Q of Rn and at least two into R. And this is the statement: if f restricted to the surface has a local extremum at some point A and the gradient of g does not vanish, then the gradient of f at A and the gradient of g at A are linearly dependent, and the quotient of the ratio of proportionality is called lambda. So, okay, so the gradient of f is proportional to the gradient of g. Okay, so this coefficient of proportionality is called the Lagrange multiplier relative to the optimization problem maximum of f over g minus 1 of 0. And in some definitions, you may find the conclusion written as gradient of f at A plus lambda gradient of g of A0. It's this exactly the same, but we change lambda into minus lambda. Okay, so don't worry about that. It's just a convention. So for us, a Lagrange multiplier would be this, could be 0 actually. Now, for simplicity, we'll present the proof for n equal 3 for 3 variables, but the same proof works for any n. Okay, so let A1, A2, A3 be the components of A, and denote the arguments of f and g by x, y, z. You can call them x1, x2, x3 if you like. Doesn't matter. Now, what does it mean? What does it mean that the gradient of g is not 0? It means that one of its components is not 0, but the components are the partial derivative. So we can use two notations, if you like, del 1 g of a at a, or del g over del x at a. Similarly for del 2, del 3. I find this notation a little bit easier instead of less cumbersome than but if you want, you can use this if you are familiar with this notation, but it's the same thing. Okay, so one of them is not empty. So after relabeling them, we may assume that it's the third one which is not 0. But A belongs to the surface, so G of A is 0. So now we have a smooth map which vanishes at a point, and the third component, the derivative of the third component is not 0. So this means that by the implicit function theorem, we can solve the third variable in terms of the first two. Yeah? Or if you like, you can treat a1, a2 as one variable, xy as one variable, and z as another variable, same thing. Okay, so it means that we can solve locally this equation, and we get a function of two variables, phi, which solves this relation. So here, in the notation of the previous theorem, phi was g, and g was f. Okay, so don't confuse. But if you really understood what the implicit function is about, you should not have trouble with changing notation. Okay, so we have what? We have now a function of two variables that vanishes on a neighborhood on some open set. So this means that the partial derivatives or the gradient is 0. So by the chain rule, what is the partial derivative of this map with respect to x? This is the usual chain rule that you know from first year. So it's the partial derivative of g with respect to the first variable plus the derivative of x with respect to x plus the derivative of g with respect to the second variable times the derivative of y with respect to x, which is 0, plus third derivative times derivative of phi with respect to x. So therefore, I get, so partial derivative of g with respect to the first variable times 1, plus second one times 0, plus third one times the first derivative, so derivative of phi with respect to x. And second equation, I differentiate with respect to y, so I get a similar relation. And this is true, so all these maps are evaluated at the point xy, phi of xy. So in particular, when I put x equal a1, y equal a2, and then I'll get a3 here. So I get this system of equations. First partial derivative of g at a plus third derivative of g times first derivative of f at a1, a2 is 0, and similarly for the second one. And now the assumption that this is not 0 means I can divide by this. So I get first derivative of g with, over third derivative as this guy, and second derivative or third derivative is this guy. Okay, so I will use this, I will refer to these as equation 1. Okay, now if xy is sufficiently close to a1, a2, then continuity of g implies that xy, phi of xy is close to a1, a2, a3. Okay, this is the continuity assumption. So this means that if x and y is in the neighborhood of a1, a2, then xy, phi of xy is in the neighborhood of a. But we know that f has a local extremum at this point. Therefore, as the function of two variables, f of xy, phi of xy, has a local extremum at the point a1, a2. So a1, a2 is a critical point of this map. You can call it psi, I don't know, psi h if you like, h of xy. So, but what are the partial derivative of this map? So chain rule again, same system. First partial derivative of f times 1, second derivative times 0, third derivative times derivative of phi with respect to x, and similar for this. So this is the chain rule that you know. Now we distinguish between two cases. If the third derivative of f is 0, then this is 0, so this is 0, and this is 0 as well. So the gradient is 0. In this case, you just take lambda equals 0. If not, we can solve the system and get del 1 over del 3 of f is minus del 1 of f, phi at a1, a2. And similar for the second equation. So if we compare with equation 1, I see that del 1 f over del 3 f at a is the same as del 1 g at a over del 3, and same thing for this. So Therefore, if I set lambda to be del 3 FA over del 3 GA, then we get that first derivative of f is lambda times first derivative of g, second derivative of f is lambda times second derivative of g, and third derivative of f is lambda times third derivative of g, and this is just the relation that you want to prove. Okay, so what can we do from this? I just want to illustrate, in case you don't know, you didn't encounter Lagrange multipliers in first year, I will just illustrate its use on a simple example. So here's the methodology that we will follow to maximize or minimize a smooth function of n variables with a smooth constraint of the form g of x equals 0. So first of all, if we want to be rigorous, we want to make sure that the maximum and minimum exist. And this happens, this is the case if g minus 1 of 0, the constraint is actually a compact set. So like a sphere, an ellipse, or any other compact set. Second step, we set up the system of n plus 1 equation with n plus 1 unknowns. Okay, so we search for what are the unknowns here. That's a, because we don't know what is a, and lambda. Okay, so this is just an equation, and we have to restrict a to belong to the surface. Okay, now maybe you saw it as g of a equal k, but this is not a big deal, because just if you subtract k, you get change the notation, if you like. So it's enough to deal with surfaces or constraint of this form. Okay, and now we try to solve this. Now, this system is usually hard to solve. It's not always possible to solve because it's usually non-linear in A. It's linear in lambda, but non-linear in A. So there's no formula or precise algorithm to solve it. In some cases, this is possible, and I will present an example, of course. If it's not solvable explicitly, then, and you really want to maximize your problem, then you solve it numerically. Okay. But of course, we are not going to deal with this case because this is just an illustration. So suppose that we can solve this and we find some solutions. Okay. We should, if the minimum and maximum exist, we should at least find 2 solutions. Okay, but they could be more. Now, suppose that we have k solutions. Okay. Then we evaluate f at these solutions, and the maximum value among these will be the maximum, and the smallest will be the minimum. Okay, this is the case. So let me illustrate this on the starting problem: maximize x plus y plus z on the unit sphere. So I know that there is a maximum and a minimum value because the function is continuous and the sphere is compact. And second, the gradient of g is just 2x to y to z, so it vanishes only at 0. But on the sphere, the 0 is not on the sphere, so the gradient actually never vanishes on the sphere. And therefore, we know from the beginning that we have the Lagrange multiplier exists. So we try to solve, we set up the problem. So here, just instead of a1, a2, a3, I just write x, y, z because they are unknown. So what is the gradient of f, or the partial derivative of f with respect to x, is 1. So the gradient of f is 1, 1, 1. And the gradient of g is 2x to y to z. So this is 3 equations: 1 equal lambda to x, 1 equal lambda to y, 1 equal lambda to z, and we have the equation of this. Now it happens in this simple case that we can solve, we get actually, of course, lambda cannot be equal to 0, okay, because, so x equal y equal z equal 1 over 2 lambda. And when I replace this common value by in this equation, I get 3 over 4 lambda squared equal 1, and then I get 2 values of lambda plus or minus radical 3 over 2, and therefore accordingly I get 2 candidates. So I just replace lambda by its value. So 2 lambda is plus radical 3. So I get 1 over radical 3, 1 over radical 3, 1 over radical 3, or the opposite. And now I evaluate f at this point. So the sum is 3 over radical 3, which is the radical 3. Here the sum is minus radical 3. So of course, this point will be a global maximum point, and this point will be a global minimum point. And the maximum will be radical 3, the minimum will be minus radical 3. Of course, this is so simple. There are much more interesting, but this is not a course on Lagrange multipliers, but I wanted to deduce it from the implicit function theorem, because probably you didn't prove it in first year. So this concludes the video, the chapter, and the whole course. So thank you for attention. I hope that you profited from these lectures, and goodbye.